The next slide is for strip footing. Okay, so you can see here for the uniform pressure. So you can see here the distance between the column also the same, and then the load also they have the same value, n equal to n equal to n, so that the pressure under foundation will be uniform. But for the case number 2 at the right side, if the load is n different load applied to the footing, for example they have the n1, n2, n3, so they will have different pressure from the soil. Okay, so this is the strip footing. So actually why we need to provide the strip footing? So we start the footing, the pad footing. Okay, so when you design for the pad footing, and then after you do the design for the sum of footing, and then you find that the two footing need to be combined because they have the overlapping of the pad footing, so you can design as the combined footing. Okay, so now you have the too many combined footing, and then between combined footing also overlap, so you can convert this combined footing become the strip footing. Okay, in order to reduce the uniform the pressure from the soil. Okay, so for rough foundation, we also need to design for the punching shears. For example, you can see here at the left side the flat slab, the same concept like flat slab. So, okay, so if the thickness of the footing or the slab is sufficient to support for the punching shear or shear acting to the column, so we can use this type of the flat slab. And then if the shear force, the shear strength of the slab or footing is not sufficient, we need to make it area at the high stress with the thicker slab. You can see here they have the downstand beam here, and then the other option to have the upstand beam, so means the area near to the beam will be thicker as compared to the other location. Okay, so the simplest type of raft is the flat slab number A of uniform thickness supporting the columns. Where punching shear are large, the column might be provided with a pedestal at the base as shown in this figure. Okay, the pedestal serve the similar function to the drop panel in the flat slab floor, so to increase the punching shear strength. Steps to design strip footing raft foundation. First, we need to calculate the net self-bearing pressure and required base area. So the net self-bearing pressure is the bearing capacity of the soil minus the self-weight of the footing or foundation. And then the required base area need to be calculated by using the serviceability limit step, so SLS load. Okay, after that calculate the ultimate column loads, the NED, so by using the ULS, ultimate limited load, and calculate the S pressure. So the air pressure will acting upward to the foundation. So in this case, we need to provide the reinforcement bar inside the foundation by using these two loads. The column loads with the direction of downward, and the air pressure with direction of the upward. Okay, so this combination of load must be able must be resisted by the reinforcement bar. After that, calculate the VRD maximum, so means the shear resistance of the footing itself or the foundation itself, and then the value must be higher as compared to the NED. NED is the ultimate limit that load, ULS load, come from the each of column. So by using this equation, and then after that calculate the transverse and longitudinal bending moment, and then calculate transverse and longitudinal reinforcement bar, and then check for the punching shear with distance 2D or 1D from the first of column. The next step, the next slide is to design for the pile foundation. So you can see here we have two figure here. The left figure is for the pile foundation for the pile group, okay, and then the right side is for the single pile. So the pile will distribute the pressure to the soil, so that for the pile group you can see they will have the bulk of pressure larger as compared to the single pile. And then you can see here this pile is put on the gravel, okay, and the gravel. So in this design, the engineer decide to put on the gravel because the strength of the gravel is sufficient to support for the loading. Okay, and then you can see here this the properties of the ICP piles. ICP piles in practice we also call as the span pile. So the hollow circular pile. So in order to determine the number of piles, so we need to divide the working load or serviceability load with the capacity of one pile. So for example, the working load acting to the foundation is 4,000 kilonewton or equal to 400 ton. And then after that, you need to check the availability of the span pile at the area near to your project. For example, the manufacturing has the stock for the diameter 300 mm. So by using this table for 300 mm, they will have capacity 85 ton. So the total working load divided by 85, you need to provide 475, okay, or 5 piles. So for this one foundation or one column that you need to support, you need to provide 5 piles with diameter of 300 mm. Okay, so for 5 pile, the arrangement will be like this. You can see here, they have 1, 2, 3, 4, 5, 1, 2, 3, and 4, and 5 pile. So one pile will be put directly under the column, okay, with the dimension of pile cap is L and B, okay. Then all axial load come from column are supported by piles, whereas all the moment support by the pile cap, okay. So the axial load only will be transferred to the pile, okay, because why pile cannot resist any bending moment, okay. So that's why all the bending moment will be supported by the pile cap. Then all the axial load will be transferred directly to the soil by pile. The other example for the square pile, okay, the concrete square pile. So you can see here in this table they have the pile dimension 200 by 200, 250 by 250, 300 by 300, 350 by 350, and 400 by 400. With different pile size, will have the different recommended axial working. So for example, if you want to use the pile with the dimension of 200 by 200, so the working load, the capacity of the pile to support the load is maximum 45 ton. Okay. Okay, so now design of pile cap. So to design the pile cap, we need to use the tie and strut method. So they use the truss analogy method. So means the tie will be in tension, okay, and then the strut will be in compression. So you can see here have the one column that transfer the load downward, and they have two pile here that will support vertically, and then the load will be transferred in the form of the truss, where the diagonal truss will be in compression, and then the horizontal truss at the bottom part will be in tension. So this analogy will be transferred to the right side, become the free body diagram. You can see here N is the total load or total ULS load applied to one column, and then because here we have the two pile to support, so that the support action or the load that will be transferred to the one pile is N over 2, okay. And then if the distance between these two pile is 2L, so that we can calculate by using the method of join to get the T equal to NL divided by 2D. Okay, so you can cut this one joint at the left support to get the value of T. So T is N multiplied by L divided by 2D. So please take note, 2L is the distance between these two piles. So L is half of the distance. Okay. Next step to calculate for the AS. So here you can see here the AS required is T divided by 0.87 FIK. So from the previous equation, T is NL over 2D. So that in this equation, we have the N multiplied by L divided by 2D 0.87 FYK. So you can see here in equation 10.7. Okay, and then where the pile is support on a 4-pile group as shown in the figure 10.22, the load can be considered to be transmitted equally by parallel pairs of truss such as A, B, and CD. And equation 10.7 can be modified to give required area reinforcement in each truss. Okay, so you can see here. So because for the one pile, so we have the 2 pile in the previous equation. So for the 1 pile, we need to divide this T with the 2. So you can see here, T over 2 divided by 0.87 FYK for the 1 pile, so that we have N multiplied by L divided by 40, 0.87 FYK. And this reinforcement should be provided in both direction in the bottom face of the pile cap. So we will have the 2 direction of the reinforcement bar.